Dear participants, in our last discussion on arithmetic instructions, we had studied addition and subtraction instruction. Now we will be concentrating on multiplication instruction. You see that these are the four fundamental arithmetic function that any PLC is able to implement. Now we have to look into the multiplication instruction. Another important point that I wanted to share with you is that you have to always be considerate to the fact that whether you are using a register based addressing or a tag based addressing, because this makes a lot of difference in the instruction format. So here we will be working with register based addressing. All right. Now I hope you are all very familiar with that through our several hours of discussion on that issue, and if still you are having any trouble or any confusion, you may please get back to me. You see here that whenever we are talking of a multiplication function, it actually consists of two source values. So you need to have two source value, and when you implement the function or execute the function, you will be having the product. Therefore, we can simply say that this multiplication instruction is purely an output instruction. There is no doubt in that. All right. The point is the destination. If we are using tag based addressing format, the PLC having tag based addressing format, then we can simply assign a tag in which the product will be stored. Otherwise, here we are talking about, you see, the SLC 500 family or the programming environment of RS Logics 500. Here we have to give the destination address, like you can see here, N72. I hope you can recollect that in RS Logics 500 programming atmosphere, we had seen N7, that is the integer file. We normally use this N7 to store numbers or the scaled output of an analog input. So let us not be very concentrated on the term of scaled value of an analog input, but let us restrict ourselves with the fact that here we are storing numbers. We can well recall that the values can range from minus 32,768 to 32,767. These are 16-bit signed integers, and you can see in the data files there is N7 integer. So this particular data file we use for storing our product in case of multiplication instruction. Now you see this illustration. This is the multiplication block where we have two parameters, source A and source B, where we put the data on which the multiplication operation has to be performed, and here the destination address is given N72. One important point that you have to remember, that is about the data that you can put in source A and source B, that is the data on which the multiplication function has to be performed. You must remember that both of them can never be constants. They can be, you see, they can be either constant value, they can be either addresses in which the value on which the operation has to be performed is stored, but both of them can never be constant. You have to keep this very clearly in your mind. Now let us look into this particular example, where you can find source A is 20. That means we have put the value. You can see we can put this value during programming. So this we have kept to be 20. Now, this is interesting. Source B. It is actually accumulator of a counter. So C5 itself, it shows a counter. So it is the accumulator of the counter. Now, this is not the accumulator of the counter, but the value that is stored in the accumulator of the counter. So this is one concept of register addressing. Register addressing. So whatever is the content of that register, that will be the content of source B. So let us take a live example. It may so happen that for certain operation, there is a conveyor on which objects are passing and you are using this counter C5 to count C5 10 to count the number of objects that is passing in front of a through or in front of a proximity sensor maybe. So your counter is having a proximity sensor as an input. Suppose there are 1, 2, 3 such type of objects are passing, and each with passage of each object, the proximity sensor gives a pulse. So these pulse actually increments the value of the accumulator. Now, whatever the value of accumulator is, per se, 5 objects have passed. So accumulator will be having a value of 5 in case of an up counter. So now what will the content of your destination? It will be 20 into 5, that is 100. This you have to remember. Now there is a switch. When the switch is activated, that is it is connected, it is closed, then this operation will be performed. So this is the very simple I should say illustration of multiplication instruction. Now we will be going for a more elaborate example. So here you can see I will talk about the physical condition first. There is a heater. There are two pilot lamps. When the heater is on, or you can see this pilot lamp, there are the two lamps, maybe one is red, another is green, like that. This is a tower lamp. You can see one of the pilot lamps will be on when the heater is activated, that the heater is working, and other pilot lamp will be off at that moment. Now when the heater is off, then this pilot lamp 2, you can see here there is pilot lamp 1 and pilot lamp 2. When the heater is on, pilot lamp 1 will be on and pilot lamp 2 will be off, and when the heater is off, then pilot lamp 2 will be on and PL1, that is pilot lamp 1, it will be off. This is the one perspective. Now another perspective is that you can set the temperature with the help of a thumb wheel switch. We are not using here an HMI, we are using here a thumb wheel switch through which we can feed the PLC. Okay, so we are using this thumb wheel switch to set the temperature of the oven. And what is the temperature of the oven? That can be read through this thermocouple input. We can use a J-type thermocouple or K-type thermocouple, whatever it is. Now see here that the thermocouple input is given to I013, that is the input file 013. That register contains the value of the thermocouple, that is the output of the thermocouple. Okay, now output of the thermocouple cannot be directly taken, it has to be scaled definitely. So the scaled value will be stored in I013 and the temperature value will be stored in I012. So if you are confused about this terminology I, let us go over there. You can see in the data files I1 is input. Okay, so this inputs from the ports, from the input port, and O signifies output port. So your heater, pilot lamps will be connected to O, and your input devices like your thermocouple and this thumb wheel switch, they will be connected to I. Fine. So now you see that what is the role of the PLC? The role of the PLC is to ensure that this set temperature is maintained. So continuously it will be monitoring the input condition or the input temperature of the heater through this thermocouple, and it will be continuously monitoring the temperature. Now monitoring is not the only operation that is to be performed. It has to control the on and off operation of the heater also. Okay, so you see what is the condition for this getting the heater on and getting the heater off. Let us now get back to the programming literature. You see the PLC has to calculate the upper and lower deadband. Now this deadband is a very common terminology when we are using a simple on-off control, or in control engineering terminology it is also known as bang control. So there is a set point at which we want to maintain the parameter, maybe temperature or flow or level, whatever it is, and there is a deadband. As I have said, the deadband decides the on and off limit. This is actually done to save the system from continuous disturbance. Suppose you are simply using an on-off controller and you have kept the set point to be 100, maybe on 90 degrees centigrade. You are heating an oven to maintain the temperature of water in a vessel. Maybe a very simple example. Now you see you have kept the set point to be 90 degrees centigrade and your deadband is 0, which never happens. I am just talking as an example. So what will happen? You will find that the relay, that is a part of that controller to make the oven on or off, to get the oven on or off, is continuously doing that chirping, because you have not given a deadband. See, this is a physical condition. So maintaining the 90 degree is one point. The temperature, you just cannot. You can put the heater off, but that does not mean the heat energy that is accumulated, that will be immediately off. So if you are putting off the heater right at 90 degree, immediately the temperature will rise to some extent. So that will be an overshoot like anything. The temperature may reach 100 degree because of the thermal inertia. Then you have to wait till it comes down. Right at 90 degree, it will be, when it is just below 90 degree, it will be again on. It will be again putting on the system for heating operation. So what does this mean? It means that the system will be continuously under disturbance. The relay will be continuously doing that cut like that. So you want to save your system as well as controller from this very disturbing and devastating action. For that, we actually give this deadband. Now you see that here the deadband is decided like this, plus minus 1% of the set value. So if we set a value of 100 degree, then upper limit is 101 and lower limit is 99, because it is plus minus 1% regardless of the set point value. Very simple. There is nothing to be too much worried. It is written. That is the requirement of the system. So what does that mean? That means that if the temperature is above 101 or equal to 101, then the heater will be off. And if the temperature is below 99, then the heater will be on. So you have a deadband of 2 degrees, you see. So now if it is 200, then these values will be 202 and 198. Now in case of 400 degrees centigrade, it will be 404 and 396. You can see that As the temperature rises, the deadband increases. This is very much important because when you keep on rising the temperature, the thermal inertia also increases. So you have to negotiate that. Okay, that's part of control engineering. We will not get into the detail of that. You see here, for this example, we have to have the set point at 400 degree Fahrenheit. What does that mean? That means that if the temperature of the oven drops below 396 Fahrenheit, it should be on, and if it rises above 404 degree Fahrenheit, it should be off. So this is the physical condition. The point is, the PLC is getting its input regarding the temperature of the furnace from the thermocouple, that is the temperature sensor. Now the point is, who will say the PLC about this 396 and 404? For that, this multiplication instruction has been used. You see here, we will see. What is the factor? The factor is 1%. 1%. So in order to determine what will be the result of this 1% for the input value of 400, we will be taking the help of this multiply instruction. So you see here, the first instruction used is multiply. That is actually having in one of its input 400. What is 400? The value from the thumb wheel switch. Next, there is a constant. This constant is 0.01. Why 0.01? You see, that is 1%. 1 divided by 100. Now, what is the destination of the product? N70. And what is the product? 4. So, if it is 100, it will be 1. If it is 200, it will be 2. Now, the higher limit is getting defined. The higher limit is defined simply by having an addition function. So you can see 400 plus 4. So input is constant throughout, that is I012, where the BCD thumb wheel switch has been connected. So you see here it is constant 400. Now in order to decide the upper limit, we are adding this 400 by 4. This 4 is not a constant factor. In this case it is a constant factor, but you see this can change if this set point of temperature is changed. So here in this case it will remain constant throughout this process because we have kept it to be 400 degree Fahrenheit. So in order to determine the upper limit, 4 is added to 400. So your final value is 404. It is in destination N71. In order to determine the lower limit, you have to subtract this 4 from 400. So you can see the value is 396 and your destination is N72. Well, we are ready with the upper set point and the lower set point. Now the function comes of controlling the actuator, that is controlling the furnace. In order to accomplish the same, we need to now invite some comparison functions. So comparison is a great deal of series of functions that you can cover with PLC. We will be introducing here the less than function and greater than function, as you can see in these two rungs. See here that first we have introduced the less than functions. Here by default you have got two variables. So source A we have kept to be the input of the thermocouple. So initially you can see the value is 0. Now this 0 is not a constant. The input, this is the input port actually to which the thermocouple is connected. So what you find here? You find here a scaled value that is continuously updating as the temperature is changed at the furnace. Now see here that this value, that is the input from the thermocouple in this less than block, is continuously being compared with source B, that is 396. So this source B, it contains this 396 value. Now remember here that during the programming you should not write here 396 abruptly. Now this is not abrupt because you know this value 396. You may simply ask me, sir, we can write. But the point is, do not do that. That's not a good programming practice. If suppose you change this value 400, from 400 you have made it maybe 350 or 300 or 600, whatever as per the application demand, then this value will change. Again you have to put here that value. So do not do that. You keep here this register address N72. Now what will happen? Whatever is the content of N72 is, that will be reflected here. So that becomes more generic. Alright. Now you see here that what will happen whenever the value of source A is less than this value that is contained in N72, this lamp PL1 will be on. That means this PL1 will be on. Please remember that I have not yet said that the heater will be on. That will be done in the last run. Another point. So you can see this will be on till 396 degree Fahrenheit is read by this thermocouple. Once it is equal to 396, this lamp will be off. Next, let us concentrate on the greater than block. You can see here the source A is again the thermocouple. Alright, the scaled value of thermocouple rather. Source B is the contents of N71. So this one, that is the upper limit. Okay, so unless the value of source A is greater than 404, this lamp PL2 will remain off. When it is more than 404, then this lamp PL2 will be on. So PL1 will be on till temperature reaches 396, and PL2 will be on after the temperature is crossing the boundary of 404. This you have to remember closely. Now let us go for introducing the heater in the run. This is the on off switch that has been used here. Once it is on, you can see the current will be allowed for the next part of the run. So what we have done here, this is a simple latch arrangement. You can see this PL1 is the NO contact corresponding to this lamp coil, and PL2 is the reverse contact of this lamp coil PL2. Okay, and finally this combination is connected to the heater. So let us think initially that maybe the furnace is at room temperature under normal situation. So what will be the condition then? We have put this switch on. This temperature is less than 396. So PL1, this lamp will be on. This lamp is on. PL2 is already closed. So your heater will be activated and it will keep on raising the temperature. Once the temperature is equal to 396, we may expect that the heater will be off. No, it will not be like that. The lamp PL1 will be off. When the lamp PL1 is off, you can find this contact will be open. However, since the latch is there, the heater will be continuously getting power till this temperature does not cross the limit of 404. When 404 degree Fahrenheit limit is crossed, then this PL2 will become open. When this become open, then the heater will be off and the thing will go on. So this is about this multiplication instruction, where you can see this multiplication instruction has been used only in this part, and this is the first run, and rest of the things are for deciding the upper limit, lower limit, and finally operating the lamps and the furnace. I hope that this idea of multiplication instruction is clear. Still, if you have any confusion, please let me know. Thank you. Let us now go forward with the division instruction. You see the division instruction block in this illustration. Again, you have one source A and source B. You see this source A, source B and destination. These are the three things that you will be finding by default in that block. You have to put your value of any register or any constant value that you have to put. In this particular example, you can see that this source A is accumulator of the counter C510 and source B contains the value, constant value of 2. Now see definitely that this is also an output instruction. However, there is one criticality. If we consider the division instruction and the multiplication instruction. In the division instruction, when a division function is performed, you have two things to consider. One is the quotient and other is the remainder, because remainder may be generated out of some division operation. So what will happen in that case? You see here, if the remainder is zero point 0.5 or greater, you will always find that a roundup occurs in the integer destination. Roundup, and if it is 76.8, it will automatically become 77. But if you are really interested to know what is the actual quotient and what is the remainder, that's why this division instruction has got an additional point to be remembered, that the result is stored in the destination address as well as in a math register. So you will find that the most significant words of the math register that will contain the quotient, and the least significant word that will contain the remainder. So if you are that interested in knowing the actual value of quotient and the remainder, you have to go for the math register, because you do not know if the result, whatever is the result is, suppose the result is 82. So whether it is in integer 82 or whether the actual result was 81.9, that's why it has been rounded up to 82. You do not know if you only look at the result at your destination integer address. Therefore, this facility is provided. Now you see, here again you have to be very considerate to the fact that both A and B, this source A and source B, both of them can never be constant. That will invite error. Okay, so this you have to remember. So we will be directly going to the illustration. Now here you can see that we are going for a pure mathematical manipulation in which we need to develop a program to convert Celsius temperature to Fahrenheit. Celsius temperature to Fahrenheit. You see here that we are not talking about any control of any actuation, whatever it is. So we are talking only of manipulating data, right? So we have to convert Celsius temperature to Fahrenheit. Now see that for that we have to be sure about the mathematical relation. So there is a formula. The formula is something like this. F is equal to, that is the Fahrenheit value of temperature, is equal to 9 into C. C signifies the centigrade value of the temperature. 9 into C divided by 5 plus 32. So what we need to do? We need to first multiply whatever value this C, that means the centigrade temperature is having. So that value we have to multiply by 9. Then the quotient, that product should be divided by 5. And finally 32 should be added to the quotient. Let us see what we have done in the program. So as we had already discussed, you can see first we will be using the multiplication block, then we will be using the division block, and finally we will be using the addition block. So you can see here source A is an input pin, input terminal that is connected to a thumb wheel switch. So you can see the input is 60. So the input centigrade value is 60 degrees centigrade. So initially we are multiplying it by 9 because our formula warrants that 9 into C that we have done. So the result is stored in N70. The result here is 540. Now let us come to the division block. What we will do here, in source A, we will not write 540 directly. Again, that will be a particular case. We will make the program more generic. So it will be 9N70 because the product is stored in N70. Source B is 5 because you can see that we have to divide 9C by 5. Okay. So we have divided it by 5. So in destination, we have got the final result of this division, that is 108, because 540 is divided by a constant value 5. And now I have to add this 108 to 32. That's a constant factor as per the formula, this 32. So we have given here the 32 addition block. Source A is N71. Again, I am not writing 108 directly. Let it be more general. So therefore N71, and I am adding 32 over there. So what is the final result in the destination? 108 plus 32, that is 140. So that's it. Very simply we have discussed about this division instruction. So that's all with today's session. Thank you, and for any of your confusions, please let us know.